Okay. Before we go to next topic, I would like to review some of the email protocols. As we mentioned before, for the user agent, the standard user agent, and the sender's email server and the receiver's email server, they all use SMTP protocol to push email from user agent to the sender's server and from sender's server to the receiver's server. Okay, and for receiving email, actually three. Okay, 2 or 3 major protocols are used. POP protocol. Okay, they will retrieve the email from the mailbox. Okay, which is right here from the mailbox. But POP is a relatively old protocol. So after the user agent of POP receive the mail from the mailbox, the mail will be deleted from the receiver's email server. So if you have multiple user agents, for example, you have a cell phone user agent, you have a PC user agent, you have a laptop user agent, you have many user agents. Only one of the user agent will get the email because the mail has been deleted from the mail server, so the other email agent cannot receive the mail. Okay, so after that we have IMAP, Internet Mail Access Protocol. So basically they support several different user agents. Okay, all of the agents will not delete the email from the mailbox. All of the user agents will synchronize its mailbox and the corresponding mails in the user agents. So they don't have to. So you can have multiple user agents to view all exactly the same mails folders of stored messages. Okay, so that is. But as I say, currently sometimes we don't use IMAP agent or POP agent to receive email messages. So currently, maybe the most popular way to receive mail is by using your browser. So let's take a look at this figure. Okay, so basically we have a host, okay, on the internet, and those hosts are served as a mail server, right? So basically they must have a SMTP server, right? As we mentioned before, if you have SMTP message and there is a email, right? You can push the entire email. Okay, so that is a UA. Okay, the UA can talk to the SMTP server and send the email, push the email by using SMTP protocol, right, to the email server. However, usually on this host there should be a database, because in current architecture, usually those mail are not stored in the mailbox. Usually the mailbox is implemented by using database. So those mail goes to database. And for example, you have certain amount of email, we say capacity, or email size, account size. Okay, for example, I think Gmail has 5 GB mailbox capacity for each user. So basically, they are not folders. They are basically database space used for storing your emails. Okay. However, as we mentioned before, we may have POP3 server, right? And those POP3 server can access the mailbox on the database server, and then through the internet, right? They can communicate with the POP3 agent by using POP3 protocol. So this POP3 agent, user agent, can use POP3 protocol to communicate with the POP3 server, and the POP3 server can retrieve the mailbox from the database, and those emails are obtained from the SMTP server, and again from the SMTP user agent, right? So the mail is from the right hand side to the left hand side to the right hand side, and of course you can use IMAP server. Those IMAP server can also retrieve the mailbox implemented by the database server, and then talks to the IMAP user agent. And of course, the protocols between them are IMAP protocol. So that is it. But as we mentioned before, POP3 is a very old protocol. It can also retrieve the email in the mailbox, right? But the IMAP protocol can have multiple user agent. For example, 1, UA2. Okay, they can still do synchronization. So you can have a multiple user agent. Okay, but the current architecture might be looks like this. We have a HTTP server, and on the HTTP server there will be a lot of CGI, what is the programs run on the top of the HTTP server. Okay, and also they communicate with the remote HTTP client, which is the browser. Okay, and the HTTP server and the corresponding CGI programs, they can also access the mailbox on the database. So basically, you can use HTTP protocol to download the HTML file. Okay, so and those HTML files are created by the CGI programs. So CGI programs can retrieve the database entries and create tables, create a very beautiful UI interface, so that you can simply just open your browser and connect it to the HTTP server, and you can see your emails, but not in any form of SMTP or POP3 or IMAP. You simply just use HTTP to download the HTML files built by the CGI program. So that is the current basically that is the current structure of the mail server. So when you install a mail server, okay, usually as a whole, that is a mail server. It may contain lots of different protocols: POP3, IMAP, HTTP, SMTP. Okay, each different protocols, they have different functionality. Okay, they support different protocols. Okay, so before we go to next topic, I would like to show you some example of an email So let's take a look at this one. So here you can see that is my Gmail account. Okay, so you can take a look at here. Here's a button right here, and in English, there should be a button called Show Original Message. Okay, which is right here. Okay, Show Original Message. So right here, all starting from this specific bit to the end of this bit. Okay, those are emails received by my server, by my email server, which is Google's email server. Okay, but I simply just use a web browser to retrieve the email right here. And however, of course, those emails are maybe they're stored in the database or stored in some folders, but the CGI programs of the Gmail, they will present those emails in a much more user-friendly way. So you can see those figures, those tags, those colorful tags right here. But basically, the email itself looks like this. Okay, looks like this. And as we mentioned before, right here. Okay. As we mentioned before, the mail message format is under RFC 2822. So basically, the text right here are defined by RFC 2822. Okay, so as we mentioned before, there should be some headers. So those are headers of, I think it ends right here. I think it ends right here. Those blue texts, they are headers of RFC 2822. Okay, of course there are too many headers, but there are some important headers. For example, when this message has been sent or received, and let's see here, what is the subject of this email, where the mail should apply to, and where this email comes from, and what is the date of this email being sent. There are some other headers right here, but some of them are just too complex. Okay, but basically, according to IFC 2822, there should be some headers to, from, subject. Okay, you can find here, and right here from, I think from here, from this line. Okay, there's a empty line right here. So from this line, it is the from this line. Okay, that is the message body of this email. So you can see that in our textbook, in our slide, there are only 3 lines of message, right? But actually, an email can be very, very long, thousands of lines right here. And you can see that there's a very specific, we say, delimiter right here. It specifies that there are several different parts in this email. Okay, as we mentioned before, right here, okay, messages area. Okay, sorry, right there, body. The body itself is a message, and we I think it's right here, Okay, the SMTP, multiple objects sent in multi-part message. Okay, so right here, the orange line is the delimiter of multi-part message. So on the top of this orange line, those are headers. But there are several different. I think that in this email example, it has 3 or 2 different parts right here. Okay, you can see that. Okay, those messages. Okay, the first part is a plain text right here. It's chart set is UTF-8, so you can write Chinese in here. But as I mentioned before, SMTP protocol or the RFC email message, they only support ASCII code, right? So there should be a transfer encoding method right here. It is a quote. Quote is a function provided by most of the language, most of the programming language. So you simply just put all your message in this specific function, and output will be right here. Okay, so as you can see that there are some strange tokens right here. For example, equals C2 equals B76. Basically, they are encoded characters. So there we have another function called unquote. Unquote can transfer all those non-ASCII characters back to those unquote functions can decode those characters back to UTF-8 characters. Okay, so that is okay. The next part is right here, so we can see that there's a line right here. So the next part is an HTML file. Basically, the email you wrote in your email agent, Outlook or iMail, something like that, your cell phone. Basically, the email itself is in HTML. So basically, you can see that there's your HTML file right here. So the colors, the white space, the images, they will be written in HTML file, so that your browser can easily display those messages, because by nature browser can display HTML file. So currently, most of the mail are written in HTML. Okay, so that is the second part, and so on and so forth. And you can add a lot of different parts. For example, attachment. If you attach a file in your mail, the attachment will be another part. Okay, another part. So in HTML file, in HTTP, one request get one response, right? And HTTP client will pull that specific object from the server, and one object in one response. However, in SMTP, you can see the example I show you. Lot of different object, images, text file, HTML file, CSS file, attached file, PDF file, all the file, they are all encoded in one single email message, but they will be divided in different parts, and they will encode it in different way. Okay, so after you receive this email, okay, your email user agent, okay, or your browser will try to parse the multi-part messages and see, for example, there is attachment, so the attachment will be shown in some place, right? So they know how to deal with the multi-part message, but all the messages will be in only one single message, unlike HTTP protocol. Okay, if you have 10 different objects in HTTP, you have to establish 10 different requests and response. But if there are multiple messages in one email, there are only one email message, because those messages can contain different parts. Okay, so I think that is the first, that is the last thing I would like to share with you. So that is email. The next part is domain name system, DNS server. Okay, basically, as we mentioned before, if you want to communicate with a host to open a socket, okay, you have to know the IP address of this host, right? But usually, as we mentioned before, we use IPv4, right? IPv4 has 32 bits, so we have more than 4 billion different IP addresses. So it is very difficult for us to remember the IP address, right? So usually we have name, okay, something like this one, cs.ms.edu. That is more user-friendly. So human can remember what is the name of this host. But since we have IP, we have name, so we need a service that can help us to map between IP address and its corresponding name and vice versa. So that is why do we need such kind of domain name system. Okay. Of course, you can set up one single database server that store all the mapped IP address and its name. So we have nearly we have nearly 4 billion entries to record all the corresponding IPs and its name, right? But it is not that we use this word right here. It is not scalable, right? Because if we have only one single server to do such kind of mapping, what if this server is crashed? What if the bandwidth is used by, for example, denial of service attack? So ideally, we should have a distributed database, or we call many different name servers, okay, to store all the information about name and its corresponding IP. Okay, so this protocol is part of the application. Is an application layer protocol. Try to solve the names of an IP or vice versa. Okay. So next part. Okay. So the service should have translation between name and IP address. Okay. We will talk about this later. Okay. Isn't too early to say those things. Okay. And as we mentioned before, it is not good to use a single server to do such kind of services, because we have single point of failure. If this server crashed, then all the internet will crash. Okay, and then because there, I think it's right here. Okay, right here. Comcast is a cable ISP in United States, and its server, okay, alone will receive 600 billion query. Query means I would like to check I would like to resolve the IP address or the host name per day. So that would be a large amount of queries. Okay, Akamai is another CDN server company. Okay, it has 2.2 trillion DNS queries per day. So it is not possible to use single server to provide such kind of services. Okay, so we need certain decentralized database, and it is very difficult to maintain one single server to support centralized DNS. So we don't do so. Okay, because of those reasons, we don't do centralized DNS server. We use distributed DNS servers. Okay. Okay. We will skip this page because we will talk about the concept in the following pages. Okay. So we have a distributed database. Okay. So for example, if I would like to check, I would like to know the IP address of www.nccu.edu.tw, right? So the first things I would like to know is, okay, it ends up with .tw, right? .tw. So from the hierarchical view, hierarchical database, there should be one. So I should draw right here. .twdns. There should be a bunch of DNS servers that manage all of the names that ends up with .tw. There should be a bunch of servers. So that is servers right here. They know how to resolve .tw. Okay, and after that, okay, those servers will have a hierarchy. Okay, so for example, edu.tw, com.tw, gov.tw, and so on and so forth. And there should be a lot of different servers which is responsible for example, .edu.tw, .com.tw, .gov.tw. There should be a lot of servers who knows how to resolve those names that ends up with, for example, .edu.tw. So in this case, as you can see that we can further do the hierarchy. For example, nccu.edu.tw, right? ntu.edu.tw, and so on and so forth. So that is a hierarchy. Okay. First, you have to know what is your vast domain. We call it top level domain, TLD. Top is right here. Okay, top level domain. So there will be a lot of different servers on the internet. They know how to resolve different top level domains. For example, .edu, .tw, .org, .com. Of course, there are hundreds of top level domain server. They know how to find all the hierarchy underlying itself. Okay, so after that, we try to resolve .edu.tw, right? So the .tw servers, they tells you, okay, there are some servers they can resolve .edu.tw, right? So after that, we have to resolve nccu.edu.tw, and then those servers right here, they will tell us some servers, okay, go to ask them. They know how to solve nccu.edu.tw. Okay, at the end right here, if this server, okay, if this one, blue one, this server, they know how to solve any, so any, that means there's no more hierarchy under this specific server, and it knows all the, no matter what is in front of this this domain. Okay, then we call it authoritative name server. It's right here. The name is right here. Okay, but there's one important thing is that there are hundreds of servers that can resolve top level domain, but when you want to contact with this top level domain server, how did you know where those servers are? Because there are hundreds of top level domain. So let's take a look and right here. Okay, for example, you can simply just find top level domain, and you can see that we can find Wikipedia right here, and you can see that here is a list. Okay, list is right. There's a list right here. In early 90s, 1990s. Okay, there are only few top-level domain. For example, right here, as you can see, .com, .org, .net, .international, .edu, .gov, .military. There are only that few top-level domain at the first beginning. Okay, but after that we have, of course, there are one old top-level domain which is ARPA, represent ARPANET. Okay, but after that we have country code top-level domain. So currently we have 255 country code top-level domain. For example, TW is the country code top-level domain. .jp is for Japan. .uk for United Kingdom. DE for Germany, something like that. We have hundreds of top-level domain. But but currently we have even more top-level domain, but we seldom use those top-level domain because no one want to use them, because although we do have those such kind of top-level domain, but we seldom use those domain. Okay, currently we simply just like .org or .com. Okay, so for our operating system, if one of my process want to communicate with the remote host, for example, www.nccu.edu.tw, the operating system should help the process to figure out what is the IP of this name. Okay, so first the operating system should find which server responsible for the .tw. However, there's one specific role right here. It's called root DNS server. Sometimes your operating system does not know where your operating system should contact to, because there are hundreds of top-level domain servers. So theoretically, there will be 13 root DNS server. Those DNS servers, they only responsible for for resolving top-level domain. So those 13 IPs, 13 hosts, they know where to find the server who can resolve .tw, .edu, .org, .com, .uk, .jp, something like that. Okay, so right here, it's of course in the very first beginning there are only 13 root server, but you know, as those 13 root DNS servers, it is not possible for them to serve all the hosts. For example, 4 billion hosts on the internet to do such kind of name resolving, right? So basically we have hundreds of replica. It's right here. Hundreds of replica, okay, to do such kind of, for example, a load balancing job for these 13 logical root name servers. Okay, so I think that is, and ICANN, it is the organization who manage those DNS servers. Okay, and of course those replicas may be replicated by the ISPs, by the colleges, universities. There are a lot of different organizations will help to replica those root server, or they will try to set up the top-level domain servers. And for example, .tw is of course managed by some organization in Taiwan, right? That organization is TWNIC, which is exactly the same as what we show you in the very first class, that we show you a figure that how different the connection between different ISP, right? That is the same organization to create that figure. That is TWNIC. We also rely on TWNIC to help us to manage the .tw top-level domain. Okay, so that is. So, and again, we have several top level domain. It is in some way, it is in hierarchy, right? So those 13 root DNS server IP address are hard-coded in your operating system. So even you have a fresh operating system, fresh computer, they know where to find these 13 root DNS server because they are hard-coded in the operating system. So after that, they know where to find the top-level domain servers, okay, to solve.com, to resolve .org, .edu, something like that. And they will further ask, okay, what if I would like to find amazon.com? And those .com DNS server will tell you where to find the DNS server who is responsible for star.amazon.com, and so on and so forth. And again, at the end of this hierarchy, okay, there will be authoritative name server. Okay, usually those also authoritative name server are built by the organized, built by the university, by the ISP. Okay, because they are the leaf of this hierarchy. Okay, so providing authoritative host name to IP mappings for the organizations named host. Okay, usually they are maintained by the organization, but you can still maintain by the internet service provider as well. Okay, so for example, in NCCU we do have an authoritative name server in the computer center, and its IP address is right here. Okay, so every time when someone wants to contact, for example, everyone who want to contact with www.nccu.edu.tw, the first they have to ask the root DNS server where to find .tw. So there should be a TW servers in this hierarchy. Okay, so you further send a query to those servers and ask, okay, how do I resolve .edu.tw? So those servers, one of the servers will respond, okay, say, okay, I know someone who can resolve star.edu.tw. Star right here means wildcard. I believe you know that. Okay, so basically these machines, okay, those machines are in, I don't know, maybe internet. I think it is internet, Taiwan Academic Network. Okay, some servers were responsible for resolving all the wildcard.edu.tw, and then they will tell you where to find nccu.edu.tw. And most likely this server will be exactly this one in our computer center. And this specific authoritative name server can resolve anything .nccu.edu.tw. It's right here. Okay, so that is the hierarchy, the root server, top level domain, and authoritative name servers. Okay, but page 62, the local DNS server, that is totally another thing. This is not related to the hierarchy. Okay, so that is right here. The local DNS server does not strictly belong to the hierarchy. I would like to show you by using this figure. Okay, and you can see that the blue one, okay, it's us. Okay, if possible, you can simply just remove this line because it is not related to the DNS. Okay, so it's me. We have a requesting host. I would like to query what is the IP address of gaia.cs.umass.edu. Okay, that is my query. Okay, so What is local DNS server? But actually, it is a proxy. It is very similar to HTTP proxy. Okay? Think about one thing. If you want to go to, for example, google.com, so every time you launch your browser and you type google.com, and your operating system need to figure out what is the IP of google.com, right? So it has to send certain messages to the DNS servers and to try to retrieve the IP address of google.com, right? So for example, in campus, you have thousands or even 10,000s of browsers, and they started from google.com, right? Their first page is google.com, right? So there will be thousands or 10,000s of DNS query. So similar to HTTP proxy, okay? Usually in our local area network, okay? We also set up a local DNS proxy server. Okay? It can help us to remember to cache, okay, the name and IP address mapping in this specific local DNS proxy or cache. So, okay, align with me, okay? So the first query should be like this. Me, as the requesting host, I would like to query gaia.cs.umass.edu. I want to know its IP address. So I send a query to the local DNS server. And the local DNS server check its cache. So there should be a database to cache all the mappings. And if there's no such records, so again, right here, the server, the local cache server, will further send a new request to the root DNS server. Okay, so say, okay, could you help me to find who is responsible for .edu? Okay, and how did this local DNS server know where those root DNS server's IP address? Because as I mentioned before, those IP addresses are hard-coded in the operating system because there are only 13 root DNS server originally. So for example, this root server is 1.2.3.4. Its IP address is like that. So the local DNS server can send an send a DNS query to 1.2.3.4, which is the root DNS server, and ask who is responsible for .edu. And then the server, okay, 1.2.3.0 will respond that, okay, 5.6.7.8 is responsible for .edu. So this one is 5.6.7.8. So after that, again, your local DNS server will send another new DNS query to that 5.6.7.8, this top level domain DNS server, because it is responsible for .edu. So it will ask the next question: who is responsible for umass.edu? And this 5.6.7.8 will respond its answer. Okay, it may say, okay, 9.10.11.12 is responsible for umass.edu. So this specific machine who is 9.10.11.12 is responsible for star.umass.edu. Okay, and then again, okay, as you can see, your local cache DNS proxy will send, okay, who is responsible for okay, but that's a little bit different right here, okay, because the 9.10.11.12, this specific IP, this specific host, okay, it is the last hierarchy, okay, the leaf of the hierarchy. So basically, if this specific DNS server is indeed the authoritative name server, and the response will say, okay, you don't have to ask any others because I'm the last server, DNS server in this hierarchy. So simply just ask me about your question. Okay, so if that is the authoritative name server, the response will say, okay, I am the authoritative name server. I can resolve any .umass.edu. So after that, the response at the seventh step, it may get the answer of this one, no matter how long or several different dot in the domain name, okay, as long as it ends up with umass.edu, and this authoritative name server can resolve the answer. So the answer might be 13, 14, 15, 16. It says, okay, I know gaia.cs.umass.edu because I'm the authoritative name server. You don't have to ask somebody else because I know all the answers. Okay, and after that, the answer goes back. For example, 13, 14, 15, 16. Okay, answer is gaia.cs.umass.edu question mark, something like that. So of course, this local proxy DNS server will cache, okay, this pair, which is gaia.cs.umass.edu and 13, 14, 15, 16. This record will be cached in the local DNS server. So as I mentioned before, local DNS cache server is not part of the hierarchy because root DNS server, top level domain server, and the authoritative name server is the hierarchy, but the local DNS server is not. But by cooperate with each other, we know how those we can obtain the result of this mapping. Okay, and the architecture right here is basically all the question is most of the question is asked by the local DNS server. So it is a iterative query, and you can see that there's another query resolution. It's called recursive query. So basically, it's simply just read those lines. Okay, ask the local DNS server. Okay, what is gaia.cs.umass.edu, right? And then the server will ask the root server, would you please help me to resolve this IP address? And then they will further ask the top level domain, and it will further ask the authoritative name server, and then come back and come back and then come back, and then finally go back to the original host who want to know where who is gaia.cs.umass.edu. So that is called recursive query. And of course, every time you do recursive query, the root DNS server will suffer from a very large, heavy query process, right? Because it is not that because all the processing will go through the DNS, root DNS, the TLD DNS server, and the authoritative DNS server. So you can see that for the TLD, top level domain server, it has to maintain several different connections with several different people, right? But for the eternal rated query, all the functions relies on the local DNS server. But local DNS server only serve people who is in the van. So relatively, this is not that heavy loaded. But for the recursive query, all those root server, TLD server, authoritative name server, they have to participate in such kind of processes. It's very heavy loaded. Okay, I think you can see the difference between them. Okay, and as I mentioned before, every time you do such kind of query, you simply just remember the mapping in your local cache, which is more convenient for you, no matter it is a simple cache in your requesting host or is it the cache in your local DNS server. It's more convenient for you to do further querying. Okay, so that is, and for every records cached in your proxy or in your local cache, there should be a TTL, time to live. It is a time that the cache entries timeout disappear after some time. Usually is in second. Okay, so if you if you figure out the IP address of gaia.cs.umass.edu, okay, your local cache server, your local cache at the host, your proxy, DNS proxy, they will maybe remember those mappings in, for example, 10 minutes. And after 10 minutes, if no one query such kind of entry, they will delete these cache records. Okay, so that is this one. Okay, let's stop right here and we will continue next hour.